Everybody managed to find the sum one way or another, right? All the sums you need? Right? Apparently, if you're continuing down that, everybody found the sums you need, the 2,563, blah, blah, blah. Let me just show you, if you get what I'm about to do, then you can do it this way. If you go to Stat, Calc, 2 bar stats, it can do 2 lists at once. Where are the lists that I want the sums? Which lists do I need the sums for? L3 and L4. Okay, so I'm going to do that on L3 and L4. If you have the newer calculator, you just have to put in there L3, L4, where it asks you for the 2. That sum of x, that's the first list. And the second list, remarkably enough, it's going to call it y. So when you give it 2 variables, it calls them x and y. So the first one is the sum of the third list, which is the mean. And the second one is the sum of the fourth list, which is part of the standard deviation. Now, if you didn't get that and you found the sum anyway, great. Do it the other way you did. That's just a little shortcut. Oh, scheiße. This thing is so free. Go. Oh, bless you. What was that? 47.17? This is 2,600.
563.
Oh shoot. 2563.37. Okay. This is a valid probability distribution.
Yes.
No, for sure it's a valid probability distribution. Yes, why? Good. Each p of x between 0 and 1, and sum p of x is 1. I like it. So you just got to say those two things in some way. Don't say they all add to 1. Like, what the hell is that? You know, all the numbers over there. What's probably a kid's picture believes there will be at least 25. Well, I could be kind of silly and add these all up, or I could just realize it's 1 minus that, which is the same idea as probably at least 1 is 1 minus none. Same exact idea. Just 1 minus the thing you left out because you know they have to all add to be 1. I like it. By the way, if these added to be 0.999, if they did, would that be okay? Yes. So be careful when you say this. If you say the sum is 1 and it really isn't 1, then you really didn't check it. So you better believe I'm going to put something that adds up to be 0.999 just to make sure you actually do it. But this one came out to be 1 if I remember correctly. So this would be 1 minus 0.07 is 0.93, or if you add them all up, you eventually get to 0.93. I like it. And now I just got to know, this one we know already. 47.17. The mistake people make on this is for some reason they square, but the sum of these is 2,563.37. I don't have to square it. It doesn't say to square that sum, it just says put the sum here. Minus what?
47.17.
Now that one has to be squared. That's the second thing people mistake. Some people put too many squares in there, and some people don't put enough squares in there. And you're like, oh my god, mathing your squares. So what do you get when you do that?
131.3.
I get all kinds of things, right? 2563.37 minus 47.17 squared. 338.3611?
Yeah.
And then if you take the square roots, you get the standard deviation.
18.39.
What do you get? 18.39. 395. I like it. All right. So on average, these kids thought they were going to retire at 47. Possible. Some people are retired at age 30, but those are called lucky. Can't all be lucky. That's the standard deviation. That's how far off their guesses were from the center for when they're going to retire. Now here, this sounds very familiar, but it's going to have a little slightly different way to do it. The middle is the mean, of course. If I go one step up, where do I get to? 65.5 blah blah blah. Take one step down, I get to 28.7 blah blah blah. Sorry. All right. Why does it not really matter that much with the decimal parts? Because all my data is whole number parts, right? So what I'm going to take anywhere from 29 up to 65, right? So what did I catch? I caught 25. No, I didn't. I caught 25 is down here, Jeff. I caught 40, 60, 65. Now I didn't just catch 3 data points. I caught a percentage of 40s, a percentage of 60s, and a percentage of 65s. So what percentage total did I just catch? Yeah. 3, 5, 60, no, 70. Isn't that 70? Yes. 70%. Does everybody see where 70% came from? Because what did I catch? All the 40s, all the 60s, all the 65s. So if you catch the 40s, well, you caught 25% of the data. And I caught I caught an additional 60. And I got the 65. So an additional 29%, so a total of 70 when you put those all together. It's a slightly different way to do it besides if they give me a list. But I should be used to this. I don't have to divide by how many there are because, again, the probabilities already have that built in. Now this one, I wanted to, everybody get to part E. What percentage think they'll retire before 50? What percentage think they'll do that? Yeah, what is this, 53%, I like it. And how many total kids did I talk to? 200 kids. They're all like, who the hell are you, mister? 0.53. I didn't actually talk to 200 kids, thank God. That's 200. Do you guys see what I'm doing?
Yes.
53% believe so. So 53% of 200 is 106 kids thought they'd retire before age 50. They might. They might not. I don't know. Next few decades we'll be working into our 80s. That's your world. Sorry. Yeah, I think that's plenty. What do you guys think? Yeah. Yes. Yes, Jeff. My God. All right.